All right. Very good morning, ladies and gentlemen. Very good morning, one and all. Once again, really appreciate you taking time to be with us this morning. Appreciate you joining us for the introduction to developing applications with NVIDIA DOCA on Bluefield DPU's webinar. Right, this morning, I'm excited to welcome all of you. My name, by the way, is Victor Ng. I'm the editor-in-chief of Digicon Asia. And I really want you to understand that this session is really useful for all of us. We will be able to demystify NVIDIA's DOCA software development kit and demonstrate the power and simplicity of application development over Bluefield DPU. Now, if you have any questions along the way, there's a Q&A button at the bottom. Just key in your questions there, and at the end, I will raise the question on your behalf, and our experts this morning will respond to you. The experts with us this morning is Mr. Scott Ciccone, who is the Director of Product Marketing for DOCA at NVIDIA. Right. We also have Ms. Anuradha Karupia, who is the Technical Marketing Engineer for NVIDIA's Bluefield DPU and DOCA. So with these two experts here with us, I believe you will find this session really useful. So to make it interactive, we hope that you will keep your questions coming in. And just a little bit of housekeeping now. As you can see, this session is being recorded. That's why we have to mute everyone if you find useful. So please hold on to the end. So without further ado, I really want to get the experts on stage this morning to speak to you. Right. So first to come on with Mr. Scott Ciccone, who is the Director of Product Marketing for DOCA. Now he has been with NVIDIA for the last 2 years after joining the Cumulus Networks acquisition in 2020. Previously, Scott has more than 20 years experience in product marketing and management at Palo Alto Networks, Cisco, and Sun Microsystems. So we are really indeed honored to have him on screen and on stage with us this morning. So without further ado, I just hand the stage over now to Scott. Scott, please.
Thank you very much, Victor. I appreciate it. And let me just pull my slides up very quickly here.
No problem.
Okay, hopefully you can see that, and I'll put it in full screen mode. Okay, well, first let me thank everyone for joining us today. Really excited to have you here. Anuradha and I are very excited to speak with you all about developing applications with NVIDIA DOCA on Bluefield DPUs. So I'm going to start by giving you some initial background and what's created the need for the DPU, and then we'll cover DOCA in a bit more detail. And let's see, is that not sharing? There we go. Are you able to see my screen now, Victor? Sorry, I just got a message on my screen. Great, thank you. Okay, so, and then I'll share with you some exciting partner ecosystem use cases that I hope are going to get you excited about getting started with DOCA. And then Anuradha is going to spend some time discussing more details about how to develop applications. So without any further delay, let's start by getting a little bit of background. So the data center is continuously evolving. Cloud computing and AI are driving fundamental changes in the architecture of data centers. Traditionally, the data centers ran in these monolithic software packages. Virtualization drove software-defined data centers where networking, security, and storage were software that was running on a CPU. And although it was easier to manage, the added CPU load made it difficult to run applications and added additional load on the CPU. And if you look on the screen, that's the part shown in the dark gray portion. Later, these applications were disaggregated into smaller microservices that were able to work with things like CI/CD methods. And data centers became swamped with east-west traffic that was generated by these microservices. The next thing that emerged was deep learning, which is, as you know, compute intensive. And AI has become the forefront of the evolution of the data center. So now the networking load is growing exponentially, with infrastructure as one of the largest workloads in the data center. And that has led to a need for a new chip to be designed. And this is where the DPU comes in. And it actually solves the #1 software-defined data center problem, which is a problem essentially of efficiency. And we'll talk a bit more about that. Okay, so let me talk now about the Bluefield DPU. And this may be your first time hearing about this. If not, then this may be a little bit of a repeat, but I think it bears mention. So as you know, about 18 months ago, NVIDIA introduced the Bluefield DPU. Bluefield is a new class of processor that specializes in data center infrastructure processing. So when we talk about Bluefield, we talk about its ability to do 3 primary things. The first is offload, also accelerate, and third, isolate. So offload, accelerate, and isolate. And we'll talk a bit more about that as we go through some of the slides. But to better understand the role of the DPU in the data center, let's first look back at how enterprise data centers have evolved in the last 2 decades. So in legacy IT environments, all data center infrastructure services, including networking, storage, and security, were deployed on dedicated hardware appliances. And these appliances were typically fast, but also expensive and proprietary. If you fast forward to today, in today's virtualized and containerized environments, these infrastructure services run primarily as software elements on every node, side by side with the tenant applications. And although this has been a great evolution of the data center, running those infrastructure services on the host CPU steals away the precious CPU cores. In fact, the hypervisor itself consumes about 30% of those CPU cores, which impacts application performance. It reduces efficiency. And if you're talking to the hyperscale guys, these cores that are being consumed are cores that they can't sell to their customers. So this directly hits their bottom line and is a big reason why they've been early adopters of the DPU. Another challenge the existing architecture presents is that business applications and infrastructure workloads both run on the same environment, being the host CPU. So this increases the attack surface on the system and also creates some operational challenges. So again, the role of the Bluefield DPU is to offload, accelerate, and isolate, and more specifically, offload and isolate the infrastructure services from the host CPU and accelerate them in hardware by leveraging the purpose-built hardware accelerators within the DPU. And this effectively creates, from a security perspective, a new security perimeter in every host. And this actually has some pretty incredible benefits that I will dig into a bit more during our session. So let's explore some of the benefits for deploying DPUs in the enterprise. So it basically starts with accelerated performance. Bluefield features a broad range of hardware accelerators for software-defined networking, storage, and security. The result is industry-leading performance for many use cases. Next thing is the cloud scale efficiency, which is achieved by offloading infrastructure workloads from the CPU to a specialized processor in the DPU. Data center CPUs are freed up from the infrastructure tasks to run more enterprise workloads, which provides better performance and scaling, and of course means a reduced TCO and better business outcomes overall. The third thing is zero trust security. And Bluefield offers a range of advanced zero trust security capabilities. I do have more detail on this, but just to give you a little bit of an idea here, zero trust cybersecurity models recognize that everyone and everything, both inside and outside the network, must be authenticated, monitored, and segmented. So with this, you can minimize the impact of unauthorized data access when security is compromised. Bluefield and DOCA offer a means to implement these zero trust principles. And with DOCA, we can actually add a layer of trust at every layer and limit access where needed. And that includes attestation, authentication, and monitoring to every data center endpoint. One key to implementing a zero trust architecture is the isolation of the infrastructure and security controls from that application domain. And I mentioned that earlier. The isolation reduces the attack surface in a system. And in case of a breach, if there did happen to be a breach, it helps to stop attackers from spreading across enterprise networks. And the last piece here in terms of the value of the DPU is about having a programmable infrastructure. So software programmability is a core value of a Bluefield DPU. And with Bluefield, you get a fully programmable and accelerated data center platform for running both modern and legacy enterprise applications. And this is really where DOCA starts to come in. So let's talk about DOCA. What is DOCA? DOCA is the SDK for the Bluefield DPUs. DOCA consists of an SDK and a runtime environment. The runtime includes tools for provisioning, deploying and orchestrating containerized services on hundreds or thousands of DPUs across the data center. DOCA essentially enables developers to more rapidly create applications and services to run on Bluefield. And it's the key to unlocking the potential of the Bluefield DPU to offload, accelerate, and isolate security, networking, storage, and management infrastructure. So we're continuously adding new features and capabilities, drivers, APIs, libraries, and reference applications to DOCA with 2 major releases each year. And essentially, DOCA is a one-stop shop for Bluefield developers, providing everything they need in one place. If you're familiar with CUDA, it's very similar to what you would expect on the GPU with CUDA. DOCA ensures compatibility. So if developers are building applications today on a Bluefield 2, we do ensure that software compatibility from generation to generation. So it does provide developers with the ability to develop on any version of Bluefield. We have Bluefield coming out later this year. We'll GA Bluefield 3. And that's going to provide confidence that their applications will work on all future versions of Bluefield. And finally, DOCA also adds the creation of a rich ecosystem of technology partners. It's growing quickly. I'll spend more time on some of these examples today, but you can see some of the partners that we're working with now. A couple examples I'll talk about: Palo Alto Networks, Guardicore, now Akamai. And in our next slide, we're going to talk about DOCA for the developer and the experience for the developer. So there's a shift required for cloud and data center developers to use the DPU. To enable the shift, we need to create a great developer experience. This is the same as what CUDA did 15 years ago, as I mentioned. For DOCA, the journey starts now. For the developer, we've created a new environment. This is new for DPU development. The 3 main pieces include, on the left side, you can see SDK Manager, then it's the developer container, and then DOCA for x86 or on the host. So SDK Manager is the tool to enable developers to easily install the DOCA packages, including the SDK components, the runtime components and tools, and also to flash or update the DPU software in the DPU card itself. The second piece is the developer container, and this enables developers of DOCA accelerated applications anywhere. So you can develop these applications anywhere in the container. You don't have to do this on the ARM processors, on the DPU, or on a host with the physical DPU. You can do this in a developer container, which emulates the ARM processor. And in the third section on the right, you can see the DOCA packages for x86, because DOCA is not just about developing applications on the ARM of the DPU. It's also about developing applications on the host, leveraging the DPU in different ways. And you can see here, our journey starts with going to the DOCA Dev Zone, learning more about what we've created and choosing the way you want to develop. And we're going to give you all the details on how to do that at the end of our session to help you get started. Okay, so if we go to the next slide, you're going to see that DOCA is not just about developers. DOCA is also an important tool for IT admins, DevOps engineers, and IT professionals to leverage DPUs in the data center. And again, DOCA is a one home for everything you need in order to use and leverage DPU acceleration in your cloud. So in the near future, we'll have all the different tools, including single pane management, whether that be Fleet Command or Base Command Manager for managing AI workloads, or eventually support Bluefields in that solution. So from our perspective today, DOCA already brings significant value to the runtime. There are applications which I'll refer to in a minute, which are enabling accelerated use cases with DPUs for admins and DevOps. And again, you don't have to be a developer in order to leverage DOCA to accelerate virtual switching or in order to accelerate encryption of the overlay network. These are pieces that are part of the DOCA runtime for the host and the DOCA runtime for the ARM. So we're providing examples on how to leverage that. And of course, with DOCA, we also refer to development tools or deployment tools, provisioning tools, management and orchestration tools, and a lot of aspects which are not just from the developer point of view. Okay. So I'm excited that just last week on May 5th, we released a new version of DOCA, DOCA 1.3. DOCA 1.3 represents a significant advancement with our Bluefield DPU software, supporting 121 new APIs, while the previous DOCA releases are already being used by over 2,400 developers worldwide in our early access program. DOCA 1.3 introduces several key innovations, and I'll just touch on these briefly. The first, we just introduced as part of Dockerflow, which is called Optimized Flow Insertion. And Dockerflow, if you're not familiar, is an API that serves as an abstraction layer API for network acceleration. I believe Anuradha is going to talk more about this in her session. Optimized Flow Insertion is a type of hardware steering that provides a new way to manage the packet steering table of the DPU, offering an increased flow insertion rate with potentially up to 10 times better performance and enabling scaling of up to 1 million rules per second. The new release also brings DOCA accelerated services, including DOCA host-based networking that enables routing on the DPU, the DOCA comms channel, which provides a secure, flexible, and efficient means to isolate communication between the host software and the DOCA services running on the DPU. DOCA Zero Trust Security Framework and the App Shield library with host monitoring, enabling security vendors to develop accelerated intrusion detection systems. And again, I'm going to touch more on that specifically in just a few minutes. And finally, DOCA telemetry streaming service for real-time visibility and platform telemetry. DOCA telemetry is also a key element in our cybersecurity platform called Morpheus, which utilizes artificial intelligence to identify malicious activity. Okay, so we talked a little bit about zero trust. So let's talk about zero trust as it relates specifically to DOCA and Bluefield. And with DOCA and Bluefield, this brings some very unique capabilities to a zero trust approach with the DPU's ability to isolate the infrastructure workloads from the CPU. So just a little bit of context, the modern data center has no boundaries and has evolved from an actual facility containing on-premise infrastructure to one that connects on-premise systems with cloud infrastructure, where networks, applications, and workloads are virtualized and spread around multiple private and public clouds. So with edge computing and work from home, the complexity has become even greater, leading to a global transformation towards zero trust. And zero trust requires that all users, devices, and applications connected to the network are continuously authenticated and monitored. So a zero trust security model means minimal trust in every portion of the data center infrastructure. Even when trusted, privileges should be kept to a minimum while protecting data in transit and data at rest with encryption. And with this, you can minimize the impact of unauthorized data access when security is compromised. So Bluefield DPUs and DOCA offer a means to implement these zero trust principles. With DOCA, we can add trust to every layer and limit access where needed. And this includes, as I mentioned before, attestation, authentication, and monitoring to every data center endpoint. Okay. So one of the things that helps us bring zero trust is this DOCA App Shield library, which we are continuing to develop. There were some new capabilities in DOCA 1.3 that just came out, but the DOCA App Shield library provides developers and security vendors of host monitoring solutions with the ability to create robust, accelerated host intrusion detection systems, and allows identification of an attack on the host. So if a host is compromised, attackers normally exploit the security control mechanism breach or breaches to move laterally across the data center networks to other servers and devices. App Shield-based security services enable security teams to monitor their application processes, continuously validate their integrity, and in turn detect malicious activity. So in the event that an attacker kills the host security agent processes, App Shield can mitigate that attack by isolating the compromised host, prevent the malware from accessing confidential data or spreading to other resources. App Shield is an important advancement in the fight against cybercrime and an effective tool to enable a zero trust security stance. So this diagram tries to depict the security flow, starting first with Dockerflow and DPI, or Deep Packet Inspection, which enable the stateful inspection traffic that is not identified as malicious is forwarded to the host software. And let's assume you have a process that the host that you need to ensure continues to operate or is not suspended, such as a host intrusion detection system. In this case, the App Shield-based service will actively monitor that process to determine any anomalies or malware or intrusion. And looking forward, we believe that we can drive AI for enhanced monitoring that identifies the unexpected and expand the cyber investigation tools to every DPU. And finally, on the right, the DOCA telemetry and Morpheus provide the reporting mechanism and any updates to the policies provided in a feedback loop back to the stateful inspection entity. So generally, I think you can see the security capabilities and the ability to offload and accelerate of the DPU are significant advances in the data center. I'm really excited to see what will happen next from a security standpoint. So what I want to do now is sort of change direction a little bit here and start to talk a little bit about some of the prominent use cases for Bluefield and DOCA. So cloud computing has been a major focus for us on the DPU journey. Bluefield's used in bare metal and virtualized cloud data centers, and more recently also in Kubernetes clusters, often running on bare metal infrastructure. The next one is cybersecurity, as I've been talking about a bit here already. Bluefield's unique ability to isolate the infrastructure workloads from the CPU enables a significant improvement in security and zero trust capabilities, as we discussed. And these were not previously available. So again, we see Bluefield used in next generation firewalls and microsegmentation and all sorts of security applications. And I'm confident we're going to see tremendous momentum here in the coming months. So HPC and AI, telco and edge, enterprise storage, and CDN also are areas where Bluefield adds significant value in terms of accelerated performance, new functionality, and more. And we do have examples of some of these. I won't be able to get to all of those today that we have in motion, but let's look at some of these, a couple of these categories a little more closely. We'll look at cloud and we'll look at security a little bit more closely. So the first here is cloud. So some of you may have heard about Project Monterey. Project Monterey is a re-architecture of VMware's cloud foundation from the hardware up to support various application requirements, such as customers that deploy modern cloud-native applications over VCF. Again, VMware's cloud foundation. So VMware's Project Monterey is an industry-wide collaboration to integrate DPUs, including Bluefield, and extends VCF to support a number of new possibilities, including improving the performance for application and infrastructure services, enhanced visibility and application security, offloaded firewall capabilities, greatly improved efficiencies, leading to better overall TCO for various deployment scenarios like data center, edge, and cloud. The ability to deploy a VMware NVIDIA jointly certified solution also should mitigate a great deal of risk from both a hardware and software perspective. So Project Monterey is leading a shift to advanced hybrid cloud data center architectures, which benefit from hypervisor and accelerated software-defined networking, security, and storage. And by offloading networking, storage, and security and management to the DPU, Bluefield can remove a significant burden from the CPU, saving, in this case with Project Monterey, the estimate initially is about 4 CPU cores. Target GA for this is planned for the November timeframe, initially focusing primarily on the networking and security components. But that will continue to develop, and we're super excited. I think this is a game-changing development. So some key advantages real quickly. Project Monterey is going to run key ESXi functions on the Bluefield DPU. The new platforms required for running modern workloads efficiently over the new composable disaggregated infrastructure. And it's great that VMware has recognized this early. Project Monterey will result in software that can use the Bluefield DPU to reinvent the data center architecture to deliver new capabilities. So some of the key objectives here, enabling peak performance, so maximizing network bandwidth, minimizing latency, accelerating software-defined infrastructure services, and again, all while saving x86 cycles for working on key applications. Also managing applications in a unified and consistent manner, simplifying the lifecycle management and reducing the TCO, employing that zero trust model that we've discussed, so delivering a comprehensive security solution without compromising performance in any way. And then, of course, enabling a bare metal cloud infrastructure. Okay. I do have another similar example, similar to Monterey, is a new use case that was introduced at GTC in the March timeframe, so very recently. And this is Red Hat OpenShift on Bluefield. So as you know, the IT world is moving to cloud, and cloud's built on containers that are managed with Kubernetes. The logical next step is to accelerate this infrastructure with DPUs to, again, maximize performance, efficiency, and security. So Red Hat and NVIDIA have collaborated to build an integrated cloud-ready infrastructure platform that combines the management and automation of Red Hat OpenShift with the acceleration, workload, and security isolation of Bluefield. And more specifically, customers will now have the ability to run OpenShift networking, the control and data path on the Bluefield. So benefits of this are similar: about 70% CPU utilization offload, simpler, more secure container management. All the updates, deployments, lifecycle management is centralized on Bluefield specifically for containerized workloads. And again, this is available now, but will GA in the Q4 timeframe. Okay, a couple of quick examples on cybersecurity. So Palo Alto Networks has an example called the Intelligent Traffic Offload for the next-gen firewall, which is powered by a Bluefield 2 in this case. It is available now. This solution is the industry's first accelerated zero trust network security solution. The primary problem Palo Alto Networks was having was scaling the firewall, the next-gen firewall, with the amount of data from next-gen workloads, such as media streaming, secure traffic from 5G, IoT, AI, machine learning. So throughput was a big issue, as well as the exponentially increasing CPU cycles that were being consumed. So essentially, we found that about 80% of the traffic that usually hits the firewall doesn't really need to be inspected because the traffic is pretty benign or considered low risk. In this case, we have an intelligent way to offload that traffic. So the DPU accelerates packet filtering and forwarding by offloading traffic from the host. It allows network flows that were previously impractical or even impossible to inspect to intelligently screen only the relevant parts and offload the rest to the DPU. So if we look at the benefit here, today if you run a next-gen firewall at 100 gig, you can only achieve about 15, maybe 16 gigabits per second. And that still consumes about 12 CPU cores. So what you find is you can go from 15 or 16 gigabits per second to almost close to line rate at 93 gigabits per second with the DPU. That's about almost a 6x improvement. But at the same time, you're able to drop the CPU consumption from 12 cores down to 0. So what that does for your TCO, and Palo Alto Networks did this calculation for us, you can achieve about 150% CapEx savings by using the DPU. And compared to what you'd spend on the DPU, this is a very compelling ROI for customers. Next example, microsegmentation with zero trust strategy with formerly Guardicore was acquired by Akamai, but microsegmentation helps to prevent security breaches and lateral movement of network traffic, and it's a core pillar of a zero trust approach. So it provides several security advantages, including bolstering of individual workload isolation, risk reduction, and simplified security management. And when you combine this with the Bluefield DPU's ability to isolate network traffic from the CPU, the Akamai solution ensures early detection while minimizing that blast radius, and has some unique and incredible benefits. First is this software is running on the DPU, so there's no appliance that's required, no agents on the server to install and manage. And by offloading the security enforcement to the DPU, the server performance is improved significantly with all the hardware acceleration. Essentially, you're getting the flexibility of modern software-based microsegmentation with the performance and efficiency of hardware-based acceleration. And that allows you to shut down the lateral movement of attackers very quickly. And finally, you get full isolation of segmentation enforcement from the workload and the CPU. Okay, so let me just take a minute to wrap this up. So if we were to summarize here, it's clear that the CPU can no longer do it all. The software-defined overhead is just too great. There's an efficiency tax that has been paid for some time now. So we must offload, accelerate, and isolate server infrastructure tasks to the DPU. To be effective, the DPU must offer hardware acceleration and security isolation, and it requires a broad software ecosystem across a variety of solution areas that we discussed. DOCA is the key to enabling those ecosystem partners to unlock that innovation. And again, NVIDIA is committed to line rate performance with forward and backward compatibility between those generations of DPUs. And as I mentioned in closing for me, before I hand it to Anuradha and Victor, the Bluefield DPUs are available for purchase. There is an early access program available for you here at the link we're showing. It's easy to sign up, and that will give you access to download software and start working with DOCA directly. And with that, let me hand it over to Victor and Anuradha. So I appreciate your time.
Thanks, Scott. I really appreciate that overview and introduction, and especially the use cases you mentioned. I think that's pretty useful for most of us. Right. Now I'd like to just hand the time to Anuradha. Now, Anuradha Karupia is the technical marketing engineer for NVIDIA's Bluefield DPU and DOCA. And in her previous role, she was a software development engineer driving the EVPN solution on NVIDIA's Cumulus Linux via the free-range routing software. So with that experience and technical capabilities, I'm sure I'm in pretty good hands this morning again, as she demonstrates to you the power of DOCA and Bluefield. All right, over to you, Anu.
Thank you,
Anuradha.
Victor.
Thanks.
Hi, my name is Anuradha Karupia. I'm a technical marketing engineer for DPU, and I'm delighted to be able to talk directly to developers and architects about DOCA. In this section, I'm going to talk about Dockerflow. I will walk you through a sample app that uses Dockerflow for offload and acceleration, and I will also provide a demo of the same application. Let me share my screen here.
Right, great. Got it.
Okay, very good. All right, let's do this now. The NVIDIA Bluefield Dpu can be used for offloading and accelerating infrastructure applications, and Scott briefly talked about that. I'm going to be talking about some of the Dockerflow libraries here. Before that, a sort of refresher about the Bluefield 2 DPU. The Bluefield 2 DPU has a Connectix 6 network card inside. It also has an ARM subsystem that is made up of 8 A72 CPU cores. It delivers up to 200 gig of network bandwidth, and it is available in different form factors. It has 2 by 25 gig, 2 by 100 gig, or 1 by 200 gig uplink. The next generation of NVIDIA DPUs, the Bluefield 3, packs a lot more processing power and brings new programmable engines. It has the Connectix 7 network card inside. The ARM subsystem has been expanded to now include 16 A78 ARM CPU cores. It has 4 uplinks, delivering up to 400 gigabit of Ethernet traffic. DOCA, Data Center on a Chip architecture, is the software framework for managing the NVIDIA DPU. It includes runtime services like host-based networking and Firefly time service. It includes the building blocks, the libraries and the drivers that you can use for offloading and accelerating your application. It comes with several sample applications that you can use as a development reference. Dockerflow is the library that I'm going to be double clicking on today. It is an API for building a generic hardware pipeline. Each flow pipe consists of match criteria and a set of actions. And these flow pipes can be chained together to build a flow pipeline that's hardware accelerated. Here I have an x86 server that is hosting a Bluefield DPU. The infrastructure application can be run on the ARM subsystem, and the infrastructure application's data plane can be hardware accelerated on the embedded switch using ASAP squared. ASAP squared is accelerated switch and packet processing technology. This allows you to hardware accelerate several networking features, such as ACL, routing, NAT, tunneling, encryption, QoS, and stats. Again, I have an x86 server here, and it's hosting a Bluefield 2 DPU with 2 25 gig or 100 gig uplinks. I'm going to briefly talk about the network interfaces and the NetDev representers that you'll be working with when you build the application. So all of these interfaces are available as net devices on the ARM subsystem. P0 and P1 are the uplink representers. And these are the real network ports. There are only 2 network ports on the Bluefield 2 DPU, and these are the real network ports. All other network functions that you're going to see are going to be built on top of these 2 devices. PFs, or the physical functions, are built on top of these 2 network ports. So there's going to be 1 physical function per PCIe device. And the physical function itself is enumerated and available on the host. And it has a corresponding representer on the ARM subsystem. For example, PF0 here is the network interface, and it resides on the host. PF0 HPF is the corresponding representer on the ARM subsystem. Similarly, PF1 has a network interface on the host and a representer on the ARM CPUs. So the PF sort of creates a network connection between the host and the ARM subsystems. Virtual functions are multiple virtual instances. So you can, using SRIOV, you can have multiple of these instances on 1 PCIe device. SRIOV is a very powerful technology. It gives the VMs direct hardware access to the network resources. The virtual functions on the host that you see here, VF0 and VF1, are mapped to representers on the ARM subsystem. VF0 is mapped to PF0, VF0, VF1 is mapped to PF0, VF1. So the virtual function creates a x86 to ARM network connection. Subfunctions, okay. So this is the next version of multiple instances. So it's very similar to virtual functions, but it is lighter and more optimal. So you can configure more of these subfunctions on the ARM subsystem. So for the sub function, similar to the virtual function, you're going to have a true network interface and a network representer. The one big difference is that the sub function's network interface also resides on the ARM. So it is sort of an ARM-to-ARM network connection. The sub function interface, the true interface, is used by the application as a network interface. And the corresponding sub function representer is used by the data plane component for programming the embedded switch. Using sub functions, you can run multiple concurrent services on the DPU. Dockerflow uses the hardware acceleration capabilities on the DPU. And the ARM, by default, controls all of the hardware accelerators on the DPU. So you can run the application on the ARM and use Dockerflow to hardware accelerate the data plane. Alternately, you can run the application on the host and still use Dockerflow to engage the programming engines on the DPU. This is sort of an intermediate step that you can use for engaging the DPU's accelerators while continuing to run existing infrastructure applications on the host. Let's double click into that a little bit. The DOCA library includes something called Dockerflow Grpc library. That is used by applications running on the host for programming the hardware accelerators on the DPU. This Grpc library is a C wrapper to C++ Grpc, mimicking the real Dockerflow APIs. So the host application can use this library to create flow pipes and pipelines as if it were running on the ARM. The Dockerflow Grpc client passes these messages to the Dockerflow Grpc server using a control virtual function. The Grpc server then uses these messages to program the hardware tables in the NIC and the embedded switch. Dockerflow can be run in different modes. These are called run modes: VNF, switch, remote VNF. Virtual network function mode is used for bump in the wire applications. And we're going to actually double click into one of those bump in the wire applications. So Dockerflow in this mode is going to program the NIC, RX, and TX hardware tables. In the VNF mode, you can send traffic from the network to the application control plane running on the ARM. And you do that using hardware RSS. So to do that, you set up a Dockerflow entry that specifies the action type as RSS and provides an array of CPU queues that you can distribute the traffic to. You can also do traffic forwarding in this mode. It is a sort of hairpin forwarding. So to send traffic from P0 to P1, you would first pair those two ports together, and that creates hairpin queues on those ports. And then you would set up a Dockerflow entry to forward the traffic from P0 to P1. So this is hairpin forwarding in VNF mode. The next Dockerflow mode we're going to talk about is the switch mode. In this mode, you can forward traffic from any network representative to another network representative. So this is the mode for accelerating vSwitches and vRouters. For example, you can send layer 2 forward traffic from VM0 to VM1. You can also send the traffic from VM0 to the network using overlay tunnel encapsulation. Another case of acceleration is the vRouter. So it's very similar to the vSwitch, except it's going to change some of the packet attributes. In this mode, you can still send control traffic to the control plane that is running on the ARM subsystem. And you do that using the same hardware RSS action that we talked about earlier. So this is switch mode. So switch mode is used for acceleration of routers and switches. The remote VNF mode is a version of the virtual network function mode that we were talking about earlier. So it is for bump in the wire applications, but in this case, the application runs on the host. So the remote VNF mode is used for hardware accelerating applications on the x86 server. We talked about this a little bit earlier. The host application uses the Dockerflow Grpc library for programming the flows and the flow pipelines. And in this mode, you can send control traffic to the host application. In the Pnf mode, we saw that the traffic was going to the application running on the ARM system. But in this case, the application was running on the x86 server, and you can still send the control traffic to it using hardware RSS. And you can forward traffic from one port to another using hairpin forwarding. So that was an overview of Dockerflow. To start using it, you need to initialize the hardware. And the hardware initialization happens using the DPDK poll mode driver. Using that driver, you're going to initialize the hardware, start the hardware ports. After that, you can initialize the Dockerflow library and map the DPDK ports to the Dockerflow ports. Once you have done that, you can start creating flow pipes and pipelines. Let's talk about that a little bit more. A flow pipe is a software template for a flow table. It is specified as match criteria and a set of actions. You can match on two levels of packet headers. You can match on the outer Ethernet layer 3 application headers and the tunnel header. And you can also match on the inner packets headers. The matched packets can be modified and forwarded to a port or to the CPU using hardware RSS. They can also be sent to another pipe for further processing. Monitoring actions such as counting, policing, mirroring can also be applied to this matching traffic. 20 bytes of scratch space is available to carry metadata per packet to the pipeline. This metadata can be used in a flow entry as a match attribute. So metadata that has been set by the previous pipe can be used as a match attribute in the next pipe. And that pipe can also set the match data for the subsequent processing. So we talked about creating a Dockerflow pipe. Creating the Dockerflow pipe does not program the flow entry in the hardware. The Dockerflow pipe is a software template for the flow table. To program the hardware flow entries, you need to add entries into the flow pipe. An entry is, again, match criteria and a set of actions. When you add the entry, you only need to specify match fields or action fields that are different from the pipe. So for example, if you created a pipe to match on UDP traffic with a variable layer for port, at the time of entry creation, all that you need to specify is the value of the layer for port field. If you have a multi-threaded application, you may need to create a queue number per core. And the reason for that is having a separate queue number at the time of flow entry creation can allow multiple threads to program the embedded switch without having to lock the underlying data structures. So this is sort of a performance enhancement. Okay, so we talked about a flow pipe, of how it's made up of match criteria and a set of actions. You may need to apply multiple processing in a specific order to a packet flow. And the way you do that is by chaining pipes. So you can set up a flow entry in the first pipe, which is called the root pipe, with an action that sends the packet to the next pipe, and so on. You can also specify the pipe chaining as a misconfiguration. So what that means is when packet is received on the port, if it doesn't match any of the flow entries in pipe 1, only then it's going to be sent to pipe 2, and so on. So these are two ways in which you can chain processing of a single packet. Another configuration of pipes is the control pipe. If you need to configure overlapping match entries in a single pipe, you can use the control pipe. Using the control pipe, you can specify the order in which you want the flows to be matched via a flow priority. But remember that the control pipe has a very limited size. It only supports 64 entries. So the ideal way to set up any sort of overlap matching is actually chaining. Okay, so a summary of what you need to do to set up Dockerflow pipes. You first need to initialize the hardware. You initialize the flow library. set up the mapping between the DPDK or the hardware ports and the Dockerflow ports, create flow pipes, add flow entries to those pipes, and chain the pipes together to build a pipeline. A detailed description of all these APIs is available as a part of the DOCA SDK programming guide. This is something that Scott talked about, and it's worth diving into a little bit. It's the optimized flow insertion that has been introduced as a part of the latest release, DOCA 1.3. This enhanced flow insertion mechanism allows you to insert millions of flows per second. And to enable that, you need to enable hardware steering in the DPDK engine, forwarding engine. And you also need to specify HWS, the substring HWS, to indicate that the Dockerflow library must engage the hardware steering mechanism. Another optimization that has been added in DOCA 1.3 is batched flow insertion. Adding flows one at a time comes with a significant overhead. So if you have to modify hundreds or thousands of flows, you could batch those updates and reduce the overhead. The way you would do that is by specifying the Dockerflow wait for batch flag at the time of flow entry addition. When you do that, the flow entry is not directly programmed into the hardware. It's instead dropped into a software queue. And you can keep adding more entries into the queue. When you're done with all your updates, you call the flush API. The flush is going to push all the entries in the software queue into the hardware. So these are two optimizations that were done to the flow insertion rate in DOCA 1.3. All right, I'm going to walk you through a Dockerflow sample application. The use case here is actually quite simple and something that almost every network engineer has had to deal with, and that's an ARP storm. So when an ARP broadcast request is sent by a VM, it's going to get flooded. It's flooded to all the other VMs in the broadcast domain. Now, if the layer 2 domain spans multiple racks, there's going to be significant replication load on the network. And a storm of these packets can have catastrophic effects. I've seen networks brought down by ARP storms. So it is important to have some sort of a storm control. One way that is done is by having policers on the top of rack switches. But the problem with these policers is that they rate limit all of the ARP traffic, including the well-behaved ones. Moving that storm control mechanism to the edge allows you to be more selective, limiting only the badly behaved senders. ARP traffic from the network that comes into the server can also overwhelm the VMs on the server. So having a mechanism, a smart storm control mechanism on the edge is useful to protect the end VM. Okay, so let's talk about how this application is going to be run on the DPU and how it's going to use the accelerators on the DPU. The ARP storm control application is a bump in the wire application. So this is going to use the virtual network function mode of Dockerflow that we talked about a little bit earlier. ARP traffic from the host is going to get trapped to the ARP application, storm control application running on the ARM CPU. All other traffic, all non-ARP traffic is simply going to get forwarded. And we're going to use hairpin forwarding from one subfunction to another to do that. The application also processes network traffic the same way we talked about how we need to do ARP storm control on traffic coming in from the network. So it's going to treat the two subfunctions, SF4 and SF5, the same. It's going to send the ARP traffic from the network to the control plane. And all other non-ARP traffic is going to be hairpin forwarded from the network to the host. So there are some prerequisites before we can run the application. First, we need to set up two subfunctions, SF4 and SF5. And I'm going to do that on top of PCIe, the very first PCIe device that we talked about, P0. Once these subfunctions are set up, I still need to forward the traffic from the host represented to SF4 and from the network to SF5. And I'm going to do that using OBS bridges, SF bridge 1 and SF bridge 2. Once the bridges are set up, you're going to see all the traffic from the host forwarded to subfunction 4 and traffic from the network forwarded to subfunction 5. And the ARP Storm Control app is going to build the Dockerflow pipeline to first trap the ARP traffic to the CPU and to audit badly behaved senders. Let's talk about the Dockerflow pipeline that this application is going to set up. We're going to build the pipeline starting from the last pipe, which is the hairpin pipe. The hairpin pipe is simply for forwarding all the traffic from one subfunction to another. The next pipe, the trap pipe, is used for forwarding selective traffic, control traffic, to the ARM CPUs. The trap pipe uses the hairpin pipe as the miss pipe. So anything that doesn't match the trap pipe, any traffic that doesn't match the trap pipe flow entries is going to get sent to the hairpin pipe. The very first pipe is the drop pipe. It's the root pipe. So all of the traffic is going to go to the drop pipe. And if there are no flow entries, or if the traffic doesn't match any of the drop flow entries, it's going to get forwarded to the trap pipe. Let's take a deeper look. So this flow pipeline is going to get set up on both the subfunctions, SF4 and SF5. Let's take a closer look at each of those pipes. The hairpin pipe we already talked about is used for forwarding traffic from one subfunction to another. So you can see this hairpin pipe is programmed with a single entry. That single entry sends all the traffic from SF4 to SF5. A similar pipe is set up on SF5, which forwards the traffic from SF5 to SF4. To do hairpin forwarding, you need to first set up the hairpin queues, and you do that using the Dockerflow port pair function. The trap pipe is used for sending the broadcast ARP traffic to the CPU. Again, it has a single entry that matches on the broadcast MAC address and sends all ARP traffic using hardware RSS to the ARM cores. The trap pipe's miss configuration is set to the hairpin pipe. The drop pipe is the one that we're going to use for penalizing these misbehaving senders. And this is populated at runtime. The application is a state machine for monitoring and detecting senders that cross configured thresholds. And those senders are penalized using drop flows in this pipe. The drop pipe uses the trap pipe as the misconfiguration. All right, let's do a demo. I'm going to switch screens here. Victor, do you see that?
Yes.
Okay, very good. So here, Bursar 1 is an x86 server, and this server is hosting a Bluefield Dpu. I'm going to walk you through some of the useful functions that you can try out for troubleshooting, and then jump into what it takes to build and run the application. I have installed the DOCA 1.3 BFB. This is the boot file on the DPU. And I've installed the Docker host repo meta package on the x86 server. This meta package is needed for installing some rshim drivers on the x86 server. These rshim drivers provide a method for connecting from the host to the DPU. They set up a host interface called TM5.net, and that's the one I'm going to use for connecting to the DPU from the server. This is the default IP address assigned to the TM5.net device on the DPU. Okay, so now I'm in the DPU. When you see the prompt with IPMI, that means I'm on the ARM subsystem of the DPU. I have set up LLDP on the x86 server and the DPU, and I'm going to use that to demonstrate some of the network connections. So we talked about TM5.net. This is the host interface that we are using for SSHing into the DPU, that it is connected to the corresponding TM5.net device on the ARM. These Ethernet ports, 65S0F0 and S0F1, they are the physical functions, PF0 and PF1. And you can see the network connection to the corresponding DPU representer, PF0 HPF and PF1 HPF. There is a Mellanox software tool package that you can also use on the DPU for getting more information about the network devices. These are the two network ports, MLX50 and MLX51. On MLX50, you can see that there is an uplink P0 and there is the host representative, PF0 HPF. So both of them are on the same network device. Similarly, on the second network device, you can see the second uplink, net P1, and you can also see the host representative. Let me make the screen a little bit bigger. You can see the host representative PF1 HPF. All of the sample applications that are there are available under opt Mellanox DOCA applications. So you can see some of the applications that Scott was talking about earlier, like the App Shield agent, DNS filter, firewall, and so on. Let's look at ARP Storm Control. That's the application that I was talking to you about. So we have that here. All of the code is here. I'm going to compile that. To do that, I need to set up the package config path for the DOCA library and for the DPDK library. We're going to be using the DPDK for the poll mode driver. Okay, now that's set up, I can build the application using Mason and Ninja. All right, the application has been built. Okay, there you go. They have the application executable here. Before I run the application, I have to set up some prerequisites. We talked about this a little bit. We have to set up the subfunctions. We have to add the subfunctions to the OVS bridges to send the traffic from the host to the subfunction and the network to the subfunction. I also need to set up huge pages because DOCA requires huge pages. That's done. Already pre-provisioned the subfunctions here, and I'm going to just show them to you. There is an IP route 2 utility called mlx-dev-m, and this is the utility that is used for configuring the subfunctions and for dumping information about them. So these are the two subfunctions that I have set up. I have set up SF4. I've set that up on top of the PCI device 0. I've also set up SF5 on top of the same PCI device. And the other thing that I wanted to talk about was the trust flag. So trust is on both of these subfunctions. This is something that is needed for programming hardware flow entries. Let's take another look at the MST status. So you can see that SF4 and SF5 are both on top of the same PCIe device. Now let's look at the traffic forwarding. I'm going to be using OVS bridges, and I have set those bridges up already. The first bridge, SF bridge 1, has the host representer and SF4. So this bridge is going to send the traffic from the host representer to SF4. The second bridge, SF bridge 2, has the uplink P0, and it has the other subfunction SF5. So it's going to send traffic from the network to subfunction SF5. So now we have traffic going from host and from the network to these two subfunctions. And the application only has to deal with the subfunctions. Let's start the application. Okay, so that is the command line that I'm going to use, and I'll walk you through that. So I have specified the two subfunctions, SF4 and SF5, that I just created as arguments using -a. -L3 that you see here, that's the log level, and 3 is info log. 4 is debug, and if you hit any problems, you can use that for debugging. For now, I'm just going to use info log, and -I is going to give you an interactive shell into the application. Okay, so here we go. We have the interactive shell, so you can run commands to dump the databases, the application databases here. Let's take a look at what's there. There is nothing. And that's expected because there are no ARP senders at the moment. So let's send some ARP traffic. Okay. I'm going to use ARPing to simulate a VM here. ARPing lets you specify the sender IP and sender MAC address. So I'm just going to use that to simulate and broadcast ARP sender. And we talked about this Ethernet port 65S0F0, so that's physical function 0. So any traffic that gets sent here is going to get to PF0 HPF on the ARM, and we have that traffic bridged to SF4. So let me send the traffic and see what happens. Okay, so the timeout is because I don't really have the destination VM, and that's fine. I'm not looking for ARP replies. I just want a bunch of broadcast ARP requests to get generated and flooded over the network, and that should have happened. Okay, there you go. The entry has been created. I'm going to simulate another sender. This is the cool thing about ARPing. I can just create thousands of senders. Let me stop this. So I have sent 10 packets here. Let's see what happened here. Okay, so we have 2 senders now in the table, but none of these senders have been dampened. Let's take a look at that table. So no drop flow entries have been installed. And the reason is at this point, the rate is pretty low. So these are well-behaved senders. One thing that I wanted to point out was the request count that you see here. This is actually a CPU counter. So it's not being counted in the hardware. It's just the CPU counting the packets that are being tracked to it. The first counter here is the total number of packets that were received. And the second counter is the number of packets that were received in the last minute. So this should have been cleared by now. Okay, perfect. So now this is all of the packets that were received. What I'm going to do is I'm going to increase the rate. I'm going to increase the rate and the number just to make it go over the threshold. Right now, I have set the threshold to a pretty low number, 100 packets per minute. So if the rate exceeds the 100 packets per minute, the sender is going to get dampened. Let's do that. Let's take a look here. You see the packets coming in. Okay, great. All right. So it exceeded 100 packets in a minute and it got dampened. So the D that you see here indicates that it's a dampened entry, and the H is that the drop flow has been programmed in the hardware. Let's see if that has actually happened. Okay, so a drop flow was created and programmed in the hardware. I'm also going to show you how to dump it directly in the hardware, but this flag here indicates that it was programmed in the hardware, and the counter that you see here is actually the hardware counter. When I created the flow, I set the monitoring flag that we talked about. So all the matching packets are going to get counted against this. Let's see if this is going up. No, it's not happening. Let's send some more traffic. Before I do that, I will show you the packets that are there on the entry. So there are 110 packets. If the drop is happening in the hardware, none of these counters are going to go up because those packets are not going to get trapped to the CPU. So let's send this. All right. I don't see anything going to the CPU. Let's look at the drop entry. You can see the drop hardware counter is going up. Okay, there you go. So it has been programmed in the hardware and it is being dropped in the hardware. Now let's take a look at the hardware flow table. Okay, so again, I'm on the DPU. You can see the IPMI in the prompt. There is a utility called MLX tiering dump that you can use for dumping the hardware flow tables. This is the embedded switch and the NIC hardware tables. I'm just gonna clone that to here. And then I will dump all of the entries that were programmed by the storm control application. Okay, here we go. So this entry, the bottom entry that you see here, that's the trap flow entry. So it's gonna match all our broadcast traffic and send it to the CPU with a mark. The rule that you see here on top, that's the drop entry. So you can see that it's for a specific sender, matching our broadcast again. It counts the traffic and drops it. That's ARP Storm Control, an application that has been offloaded and hardware accelerated using Dockerflow. Thank you.
So you're done, Anuradha?
Yes, I'm done, Victor.
Great, great. Thanks. So you can see how an application can be developed in a shorter period of time, a faster rate, faster speed, lots of automation. And well, that's really exciting for many programmers and coders out there. I hope you find it as exciting. Meanwhile, we are going in next to the question and answer stage. I think there are some questions that have been asked. So I'd like to invite both Scott and Anuradha to come back in the video. Thanks. Thanks again, Scott and Anuradha, for the presentations. We have some questions here. First one here, if I develop an application today for Bluefield 2, will it work in future versions of Bluefield?
Yeah, sure. Happy to take that one, Victor. So yeah, DOCA does ensure that forward and backward compatibility. So I know in some cases developers may consider waiting until a new version of the hardware is out, but in this case, there's no need to. DOCA does ensure that compatibility. Bluefield 2, Bluefield 3, Bluefield 4, and etc. So it's fine to develop on Bluefield 2 and have the confidence that it'll work on any future versions. Yep. I appreciate the question.
Cool. The next question then is, to develop applications with DOCA, do I need to purchase a Bluefield DPU?
Yeah, sure. I can take that one too. So as of today, the answer to that is yes. We are working on a couple different solutions that would enable remote access to Bluefield DPUs, and I'm hopeful in the coming weeks or shortly thereafter, we'll have something available that on a limited basis where applications could potentially be tested remotely. As of today, developing applications with DOCA don't require a Bluefield, but certainly to test them does require a Bluefield. So you kind of need one with the other. So in that case, right now Bluefield 2s are available for purchase and would be certainly helpful in the development process. But that is something that we're working on, and I expect that it won't be too far in the future that we have options for the folks here. Okay.
Great, thanks. There are a couple of questions related to zero trust security, which you presented earlier, Scott. So I'll just summarize it a bit, and there's one in particular here that says that the Bluefield zero trust capability is a good initiative, but can NVIDIA assist further to provide the practical approach? For example, in my organization, we don't have the ability to authenticate users' devices on an ongoing basis, and we are struggling to monitor our users post-authentication. Yeah,
so I think that it's funny because it really touches on a lot of the value of DOCA for Bluefield, right? I think what we would do is likely look to the ecosystem to develop a type of application that might enable the authentication of users, in addition to things like firewalls and intrusion detection systems. So maybe Anuradha has more detail on what that would look like today. But my thought from that question is that's potentially something where DOCA really comes in favor to help create those types of applications that would, again, benefit a zero trust approach and enable authentication of users. I'm sure there are, solutions out in there, available today, but off the top of my head, I'm not sure what that looks like, but maybe part of the Palo Alto Networks firewall solution has user authentication capabilities potentially, but those are things that could potentially run on Bluefield as well, as we begin to mature that applications that are available through that ecosystem. So I don't know if I have the answer for what you would do today and how NVIDIA would actually point you in that direction, and we can certainly look into that. But again, that to me speaks to the value of what DOCA is bringing here for those best in class type ecosystem partners to bring those solutions to the Bluefield DPU and make them available to customers that do want to improve their zero trust posture.
Scott, I can add to that. So specifically for authentication, the solutions are ongoing. But in terms of security, there are several crypto accelerators, IPsec, KTLS, MTLS, and there is these intrusion detection systems that Scott talked about, like AppShield, and the zero trust hardware boot mechanisms, secure boot mechanisms. So all of these sort of play into the crypto answers, the security solution answers that are being evolved around the Bluefield ecosystem. Right.
There are a few more questions that come in, but just to close the part on security, this last question is related to security. How can you maintain performance while implementing security?
Well, one of the things I think that's really interesting about Bluefield is the ability to offload and accelerate, as we talked about, and isolate. So the security functions basically rely on the DPU accelerators rather than CPU cycles. So essentially, when we talk about not impacting performance on the CPU, it's because that's running in the DPU now and providing that isolation capability. So you're getting better performance and improving the performance of your CPU for application workloads, right? So yeah, hopefully that answers the question.
Great. Next question, I think is addressed to Anuradha. What are the criteria for running an application on the DPU arm versus the host?
So this is something that Scott talked about a little bit earlier too. Running an application on the DPU frees up resources on the x86 server for running user VMs. So you do want to offload the control plane on the DPU, but you might already have brownfield applications that have been running on the x86 server that you just want to quickly use for programming some of the hardware accelerators. So those applications can be run on the x86 server and later on migrated to the DPU.
Right. Can you program other hardware accelerators such as the regex engine while using Dockerflow?
Yeah, the answer to that is yes. The regex accelerators are programmed using a DOCA library, DOCA DPI library. These libraries can be used along with each other. And in fact, there is a sample application called DNS Filter that does exactly that. It uses Dockerflow for programming the inline embedded switch and the DPI library for using the look-aside regex accelerator.
Right. Next question then is, would there be any compatibility issues with the hardware?
Any compatibility issues in terms of, seems like a little bit of a generic question. Is this between BF2 and BF3? Or x86 and DPU? I think maybe you're talking about x86 and DPU, so I'll take it from that perspective. You can make the infrastructure applications portable, right? For example, if you have OBS, that is an infrastructure application that can be run on the x86 server or on the DPU. And that's actually a question that's going to persist for a long time because you're always going to have mixed environments which only have the server and servers with the DPU. So you're going to have the applications be interoperable between the two.
And Anuradha, maybe it's worth mentioning how the DPU plugs into the server as well, because we didn't really cover that.
Yeah, so right now the DPU is hosted like a daughter card, right? So you can have multiple DPUs on an x86 server. By default, people typically use one, but if you want additional capacity in terms of network bandwidth or storage, you can have multiple DPUs hosted by the x86 server. You can run the DPU in this sort of embedded mode, where you can also leverage the ARM subsystem.
Mm-hmm.
Right.
And they come in different form factors for different, 1U, 2U form factors of servers as well, right?
Yeah, that's right.
Yep.
Cool. I hope that answers the compatibility question. Thanks. It's an interesting question here. I'm not sure if we have an answer for this, but I'll just raise it anyway, just for discussion. Is Docker applicable to Bitcoin mining rigs? Does it need to be in the Bluefield for it?
Yeah, that one I'm not sure of.
Yeah, that's an interesting question. I suppose you could really tap into the DPU applications for bit mining also.
Well, I guess we can't really write an answer for that. But
my first thought is that the Bitcoining, mining is typically leveraged on GPUs, which is, better at that compute acceleration, and the DPU is really purpose built for the data movement, the data acceleration. So, I don't know if that helps with that one, but a little bit of insight at least.
right. Great. So I think I have time only for one last question, and the question here is: are Bluefield DPUs available for purchase now?
Yeah, so Bluefield 2 is available. We do have inventory of Bluefield 2s. We've been selling them now for a fair amount of time. Bluefield 3 is on the horizon, and at our next GTC event in the October-ish timeframe, November, whenever that date is finalized, we'll be talking a lot more about the GA of Bluefield 3, and I'm pretty confident our CEO Jensen Huang had talked about that in the most recent GTC session. So so Bluefield 2s are available now. Bluefield 3s are coming. We're really excited about the performance and throughput gains that Bluefield 3 will bring.
Great. So I think we've come to the end of the session. I really thank you for participating. First, thanks Scott and Anuradha for the great presentations, and I want to thank all of you for staying with us for this session. You've been a great audience, and thank you for the questions. I hope we've answered most of them. If you have any other further questions, do feel free to just hit in again, and we'll have a chance to answer it via email. We'll reply. We'll give you a reply. Right. Meantime, as you can see from the slide, right, we want to thank you for participation, and we have a call to action. We have that slide, please.
Okay, and let me know if you're able to see this.
Yeah.
Yes, okay, great.
Yes, so you are invited to join the DOCA developer program today. Contact your local team from NVIDIA to discuss your use cases. Click on the link there, https://developer.nvidia.com, NVIDIA DOCA SDK Early Access. Save that link, and we hope you are part of a great community that can continue this dialogue. I mean, we can't cover everything in this session, but we hope that we can further develop that discussion and dialogue further, right? So thank you once again for being with us. I know you have busy schedules. Thank you for spending precious time with us. And once again, thanks, Scott. Thanks, Anuradha. Thank you, everyone.
Thank you for having us. Appreciate it, everyone.
Thank you.
Right. Bye.
Bye.
Bye-bye.